First of all, thank you for the invitation to speak here today. It's a great pleasure to be here. So today we're going to talk to you about something called the double copy, what it means and implications, and particularly look at its implications in classical physics. So as a brief introduction, so from the viewpoint of particle phenomenology, the best sort of theoretical modules we have for theories of particle physics are non-abelian gauge theories, so quantum field theories with a non-abelian gauge field attached to it. Within the last 20 years or so, it was realised that if you looked at the scattering amplitudes for certain non-abelian gauge theories like Yang-Mills theory and the scattering amplitudes you could write down, like quantum gravity, there's a relationship between the two of them. There's some sort of duality between them. This became known as double copy. It's first written down by Berg, Frisco and Johansson. Why the double copy has really become important, at least in the field of scattering amplitudes, and why it's captivated our imagination, is that the double copy has allowed us to calculate things in quantum gravity we couldn't do before. In particular, what the double copy means is that we can calculate scattering amplitudes from quantum gravity by essentially building them out of analogous systems in non-abelian gauge theories. Literally take a Yang-Mills amplitude, we essentially double copy it, do this process, and we actually build these scattering amplitudes in quantum gravity we want. Why that's important is that's allowed us to calculate observables in quantum gravity we couldn't do before. So we've now can calculate corrections to gravitational scattering problems up to fifth order in perturbation theory, and we can also actually, and which I think quite nicely, make connections with the experiments studying gravitational overexposure. We can actually write down and actually draw out using scattering amplitude calculations corrections to gravitational waveform diagrams, and like once I saw from LIGO, we can actually do more corrections to that. Within the last 10 years or so, it was realised that this duality between non-abelian gauge theories and gravity theories could also be seen at the level of classical physics for exact solutions to the equations of motions for both classical non-abelian gauge theories, classical Yang-Mills theory, and general relativity. This observation became known as the classical double copy. Today I'm going to be talking to you probably by the most famous example of the classical double copy, something known as the Boyle double copy, which relates certain vacuum solutions in general relativity with certain solutions in classical electromagnetism. In order to see how that works, we need to move away from our usual tensorial formulation of classical theories and move into the language of two-component spinors. How that works in general is, remember that any electromagnetic solution in the classical electromagnetism can be described by the electromagnetic field strength temperature, F nu. We take its spinor translation, which all we do by that is that for every tensorial index in our tensor space, so our nu, we replace it by two indices. So we replace it with a primed index and an unprimed index. So in this case, you see the equation here, we take our electromagnetic field strength tensor, it's a two-component object in tensor space, we move into our two-component spinor space, it becomes a four-index object. The next step that we do is we take the spinor translation of our electromagnetic field strength tensor and decompose it. So we decompose it into its constituent spinor fields, and then you see it's given by something called a Maxwell spinor, which is phi in red, phi AB, and a complex conjugate to the conjugate Maxwell field, phi tilde. If we were to play this same game in gravity, we start off with the recursive tensor, but then, as I mentioned before, we want to restrict to the case where we only have vacuum solutions. We call that in general relativity the recursive tensor for vacuum solutions, which is down to something known as the Wild tensor. From this Wild tensor, we then play the same game. We convert it into the language of two-component spinors. We get this 8 index objects here, and then again we decompose it into its constituent spinor fields. In this case, we see that the Wild tensor in spinor space is given as a combination of two fields. So it's given as a combination of something known as the Wild spinor, which is 4 object here, plus its conjugate Wild spinor. I should also mention that when we go into our spinor space, all these spinors are addressed with these eters. These these epsilons are just 2D relativity symbols, so it's based as a matrix 0, 1, minus 1, 0. What the magic of the world double comes into is that if on the gravity side we consider solutions to the vacuum Einstein equations are of Petrov type D or Petrov type N, so the Petrov types are thus a classification of solutions we can do in general relativity. Petrov type D solutions correspond to mainly solutions where we consider black holes. Petrov type N solutions correspond to solutions that are basically just space-time filled with some sort of radiation. Actually, these correspond to spacetimes that are filled with gravitational waves, the type of gravitational wave we can actually experimentally detect. By playing this game, considering our world spinner to correspond to a solution in gravity that's either petrol type D or petrol type N, we can see that you can actually build it out of something in electromagnetism. So how this works is from petrol type D and petrol type N, you can see that the world spinner is given by the product of two Maxwell spinners of an analogous system in electromagnetism. Remember that this Maxwell spinner comes from our electromagnetic field strength tensor divided by some scalar which we demand be a harmonic function, i.e. when we add the inversion on it, it gives you 0. So this is the world double copying practice. It basically tells you that for certain types of gravity solutions, we can actually build them completely out of stuff we understand from electromagnetism. The poster child for this, and probably the most simple example I can give you, is that we can take the Schwarzschild black hole in gravity, which is a petrol type D solution, and we can construct it on this right-hand side of the equation out of the product of two Maxwell fields that come from the Coulomb solution. Remember, the Coulomb solution is the electric field of a point charge, and that's related to, quite nicely, the essentially a black hole that's sourced by a point singularity. So it was soon realised that the world double copy, although it was first found for general relativity, we can actually extend it to more exotic fields of gravity. In particular, the type I'm going to talk about now, N equals supergravity. So N equals supergravity, you can think about it as general relativity plus. It's just a combination of general relativity plus two extra particles, the axiom and the dividend. One complication is when we move into N equals supergravity is that for vacuum solutions in N supergravity, the Riemann curves tensor no longer reaches down to just the world tensor. It's given by this more general object we see here, given in terms of spinners on the right hand side. So we've got, so here we've got an X spinner, its conjugate, and then what we have here, we have what I will call these mixed index fields. So it has two undotted indices and two dotted indices in spinner space, and this is its conjugate. If you really did care about calculating the world spinner in N equals gravity, that's easily obtainable by just taking this X spinner and then symmetrise it over all its indices, and then you get back this world spinner here. When the magic for N equals supergravity comes into is that N equals supergravity also possesses the same double copy structure where we have a world spinner given as a product of Maxwell spinners from electromagnetism, as you saw for just general relativity, but it also has an additional double copy structure that isn't present in general relativity. When it comes into play, it's from those mixed index spinners I showed you in the decomposition of the Riemann curves tensor, so this phi and phi tilde. So what we find is that this new double copy structure we find is it still contains this product of the Maxwell's field divided by some scalar, but it comes equipped with these, what we call these hues, these projection spinners, which are just given on either side. Essentially, they're just up to a minus sign proportional to your m sub eta symbol. So this was kind of unexpected for us at the time, because we thought, quite naively at the time, that double copy should only look like what was contained within these brackets. So when these hues came along, it was kind of a surprise to us. What kind of the importance of this result is, beyond it, well, find a new double copy, classical double copy structure for a new theory like N equals supergravity, is that in the future it suggests that we should expect to find double copies that are much more complicated than just a product of two objects divided by a scalar. What it shows us that double copies in general probably be much more nastier than we expect them to be, classically. We can also, moving on from this, take the results that we found for N equals supergravity, we can also use that to extend the double copy to work for non-vacuum spacetimes. So this was shown to work by a theory known as Einstein-Maxwell gravity. So Einstein-Maxwell gravity does general relativity, but you allow your energy momentum tensor to be non-trivial, and you also allow it to be either electrically or magnetically charged. In this case, you can actually show for non-vacuum solutions, electromagnetism, we actually nicely map them through this double copy process to non-vacuum solutions in Einstein gravity. And this was an interesting part of the process, is that before it was thought that you could never write down a sourced double copy formula. But this showing by looking at Einstein-Maxwell gravity more closely, it turns out, oh yes, you can, but it is very difficult. So how you to derive this, so I won't talk about the details today, you have to use methods from twistor theory to work out some of these results, and you also have to use some quite bespoke calculation methods for looking at classical observables in quantum field theory, which have come out in the last couple of years. Mainly something known as the KMOC formulas. In the second half of this talk, I'm going to talk to you more about the implications of the double copy. And the probably most profound implication of the double copy is that it told us about the existence of something known as a kinematic algebra. So what is a kinematic algebra? So kinematic algebras are these newly found mysterious structures that we know that gauge theories now must possess. We didn't know about them before, but by studying the double copy, we realised that gauge theories must have these new mysterious structures. We don't understand them very well. The reason is that they are defined order by order perturbation. You don't have like a complete non-linear understanding of what these algebras are. You only understand them as we go up to more and more loop orders, we get more and more information about them. So they're still very mysterious in that regard. We currently believe that the current candidates for kinematic algebras, these structures, aren't your typical Lie algebras you see in quantum field theory. We think they're more general mathematical structures, and the main candidate for that are things known as homotopy algebras, strong homotopy algebras. Previously in the literature, when kinematic algebras were first found within the first 10 years of existence, it was previously thought that one could only find a kinematic algebra for theories that have some quantum profiles, or quantum field theories where you do all the quantization conditions and write down finite diagrams and scattering amplitudes. But it can be, in some sense, you can actually realise that linear theories, so classical theories, can also have a kinematic algebra without having any interaction terms, which is kind of an interesting thing to consider. So first of all, I'll talk about one result. So the main result that helped start us off was that, that's by Kirill Krasnov and friends, is that the kinematic algebra of a linear theory, like electromagnetism, is associated with special transformations known as a diffeomorphism. So what is a diffeomorphism? If I draw your attention to the right-hand side of the board, if I was to consider a vector field, remembering that a vector field is basically where we associate a vector at every point in space-time, we can actually define something known as a field line or integral curve. So you think of electromagnetism, you have field lines, this is them. And what a diffeomorphism is a simultaneous translation along all of these field lines at the same time. So I put my hand at the bottom of the board and I move it up at the same rate along all these field lines. That's what you call a diffeomorphism. So a simultaneous translation along all the field lines at the same time. Moving back to our electromagnetism, the case we look at today, remember that its electromagnetic field strength tensor can be given in terms of vector fields. So this A, where this is the expression for abelian fields. And one thing that helps make this idea more concrete is that if we think about gauge fields more generally, we can actually think of them as being objects that are valued in two different symmetries. The first is infinitesimal diffeomorphism, so infinitesimal translations along these vector fields, but also they're also valued in infinitesimal gauge transformations, which come with their gauge groups. How we can make the kinematic algebra structure in electromagnetism become manifest, the first thing we must do is to fix our local symmetries, i.e. do a gauge choice. So in this case, we pick the gauge of light cone gauge. By picking light cone gauge, this imposes on us that we must go into a certain coordinate set. So in this case, we go into light cone coordinates, which are given by u, v, x, and y. X and y are just your usual Cartesian coordinates. U and v are just the mixing up of your time coordinate and your z coordinate, and they kind of bundle together. What's nice about going to light cone gauge is that it gives us a geometric interpretation of what our kinematic algebra is doing, what this algebra of diffeomorphisms is doing. So in the case of light cone gauge electromagnetism, we see that the kinematic algebra corresponds to so-called area-preserving diffeomorphisms, which act in either the ux plane or the uy plane. So it acts in 2D planes in your theory. So to make that idea more concrete, in this diagram, the kinematic algebras would act in this dotted plane here, go into the page, so this ux page. So what it really does is basically it corresponds to these area-preserving transformations that occur in this plane. That's kind of nice geometric interpretation of what these things are actually doing. So what is an area-preserving diffeomorphism? So on the left-hand side, I have some vector field, and I have some field lines. Let's say I draw a shape on it, a closed shape, and I say the area of that closed shape is A1. Performing the diffeomorphism, so I move all these dots up my field lines at the same rate, gives me this image on the right-hand side of the board, and I say that area enclosed by this shape is given by A2. This diffeomorphism is called so-called area preserving if after the diffeomorphism my A1 area before is equal to my A2. So basically this area bounded by these dots is conserved. So on to some open questions. So one open question we have surrounding this idea of kinematic algebras is now that we've found that linear theories somehow do have some sort of notion of kinetic algebra, which wasn't known before, You can actually go the other way around. You can actually say, if I have a linear theory, and I know it's a kinematic algebra, I can now, from first principles, construct its non-linear interacting analog. So we showed this to work for the case of electromagnetism. So we went from electromagnetism, so the example I'll show you on the previous slide, did this sort of steps from first principles, and we derived from first principles quantum electrodynamics and coupled scalar matter. So it's kind of an interesting thing that it shows that there was some sort of inheritance between non-linear theories and linear theories of the kinematic algebra, and you can exploit that to essentially build from first principles a non-linear theory. So one open question we have surrounding this is that we saw this for a specific case. How general can we make this process? So it's kind of an interesting question to ask, is that if we can write down and find a more generic formalism to do this operation from going from linear theory to non-linear theory, how can we derive essentially non-linear theories? Can we make a whole plethora of non-linear theories that we could do for just by considering linear theories know about and their kinematic algebras? A second point of further work and things to consider is that kinematic algebras aren't just for theories that are kind of a bit esoteric, but we can also see them for theories we can see in everyday life. So interestingly, non-abelian science theory, which is a theory we can actually see experimental in kinetic physics, has a kinematic algebra, but also we can see kinematic algebras for theories of fluid mechanics. So if you've ever been to the seaside or southern sea and been hit by a wave, you've literally been hit by kinematic algebra. It's actually quite interesting. So it turns out that kinematic algebras come from, you use them to describe fluid mechanics theories, and especially in particular fluid mechanics theories actually of waves going around a coast. So one piece of further work to consider from that is, can we gain any physical insight from kinematic algebras? Since we know that they correspond to, they can exist in theories that are physical, can we get any physical insight from the kinematic algebras? Or vice versa, can kinematic algebras give us any physical insights for what we see in nature? Moving back to the beginning of the talk, so the first part I talked about the classical double copy in particular, one thing we really focus on at the moment, a lot of work we over the last couple of months, is can we make the double copy work for more exotic theories? And specifically, can we make it work for regions of AGIS CFT? Can we make it work for more general supergravity theories? Can we apply it to the sitter space? Can we apply it to cosmology? So there's been a lot of interesting work in the last 6 months going on this, but this idea is very much in its infancy. So really our aim for double copy is to see how far can we push it? Can we actually make this useful for you guys in the general community? And perhaps probably a more of an esoteric point from my point of view, probably, well, for me, it's probably my thing I'm most scared about, is that so far from the classical double copy, so this relationship of mapping exact solutions from gauge theories to gravity, all the examples we have seen have been exact solutions to equations of motion, but the exact solution is that linearized equation of motion. What that means is they solve your full equation of motion, but the way it does it is that it makes your non-linear part of your equation of motion and your linear part of your equation of motion vanish separately. So you can really just get rid of your non-linear part of your equation of motion and it will still solve it. So it's not, in some sense, not really a non-linear solution. So one thing that hopefully one day we'll be able to figure out, is there any example for a classical double copy that is truly non-linear? That truly doesn't mean it is completely a non-linear thing. That's still something that's still up in the air at the moment. So in conclusion, the double copy is a relationship both at the scattering amplitudes of quantum field theory and between exact solutions in classical field theory, between non-abelian gauge theories and gravity theories. I showed you today in the first part of the talk that the classical double copy was first seen for vacuum solutions between general relativity and electromagnetism, but has been extended to work for more exotic theories like amplitudes of gravity, but also to a non-vacuum setting in the case of Einstein-Maxwell gravity. In the second half of the talk, I described to you that as a result of our study of double copy, we realised that gauge theories are much more complicated than we previously thought. They now constrain a mysterious new structure known as a kinematic algebra, and that study into that kinematic algebras are very much in its infancy, and there's lots of exciting things to go on. So if you get anything like my talk, there's plenty more to explore in the double copy, and we could do with a lot more help in it. So if you're interested, come join us. We've done a meeting. So with that, I thank you.
So, do we have any questions for Kymani?
Do you know if the double copy has been applied to like Hawking radiation information outside of black holes? I'm guessing probably not based on some of your last slides, but just.
That's an excellent he's used some scattered amplitudes methods to derive Hawking radiations. It came out in December. And with that, there may be potential applications. None of them explicitly, but there may be, now we can actually formulate it as a static amplitude problem. It may be, maybe it can be some sort of computation. But watch this space. I think there's some ideas about it yet. I'm not sure yet if they're fully formulated, but watch it. Next year, so maybe I have to answer your question.
Could you please reiterate how, regarding kinetic algebras, so you've got this group of symplectomorphisms on some light cone planes, and then how do you build the algebra from that information?
So going to the non-linear theory.
Yeah, or just generally, because I was confused how you get the gauge theory data into this. Like, how do you build these algebras generally?
That's an excellent question. So in the case of, you actually hit on it by mentioning symplectomorphisms. So it turns out that the set of symplectomorphisms for a gauge field corresponds to, if you consider the entire space of Lamb gauge for the light theory, symplectomorphisms make a small subgroup. So the whole point of the light cone gauge is that you restrict this subgroup here. Another thing about symplectomorphism is that they form a closed group under a crossover bracket. And that's kind of where your algebra comes from. So because symplectomorphisms obey some sort of crossover bracket, we can say, oh, that kind of looks like an interaction term, right? So that kind of comes from there. So because for linear theories, it's kind of a bit dubious when you call it kinematic algebras. What people normally call kinematic algebras are things that are inherently associated with the interaction term of Lagrangian for a full theory. But when you talk about classical theories, you kind of think, oh, if I bound myself in this sort of symplectomorphism space, that closed space, it's like, that's kind of like a closed algebra. But the interesting bit is that when you do this extension back into the nonlinear theory, this bit that forms the closed symplectomorphism set is the bit that actually gives you your interaction term for QED plug and scalar patterns. Does that answer your question?
Yeah, it does. And so, like, that box, is that the configuration space of gauge fields?
Exactly.
Okay, cool.
So this would be sort of like a gauge orbit in some sense.
I see.
Yeah.
And so when you talk about area preserving, is it like when you pull back the gauge field is
Yeah.
preserved?
Yeah, so in some sense, symplectomorphisms in this case are the ones that are area preserved. So I think the area preserving one is slightly bigger, I think.
Oh, okay.
But it just that symplectomorphisms are a subset of the area preserving diffeomorphisms.
Thank you so much.
You're welcome.
Can you outline what the difficulty is if you have non-vacuum solutions?
Yes. That's an excellent question. So the problem with non-vacuum solutions at the time was that you couldn't write, at least when we did the calculations, you couldn't, so when I mentioned for non-vacuum solutions, you could have like, it's a Wild spinner related to a Maxwell spinner. The problem is when you did the calculations with non-vacuum stuff, that relationship of doing this product doesn't work. That isn't enough to define it. So what happens is that when you, for non-vacuum solutions, it turns out you only get like a sort of tau state. So what happens is, can you see the board for a right on it? Yeah. So vacuum states, what happens is, so in the normal case of the vacuum solution, you get something like this, right? When you move to the non-vacuum case, which is kind of a step up from this, is that what you need to realise is you can't just have one of this, you have to have a tau of terms. So what you have is something like this. So M just lists some different sets, and then what you have here is I've got M, A, B, M, S. What you have to have a tau state. So vacuum have one of these products. For non-vacuum, you have to have a tau of these where it terminates at some end. So, for example, I'll give you an example. For the rise to Nordstrom black hole, which is a charged solution, what you find is you have two of these terms. You have a 1, A, B, C, D, 1, and then you have a second one. So these you essentially have copies of the Maxwell spinner, which you need to add on. So in this case, when it corresponds to 1, that's your vacuum ion, and this is your non-vacuum. What I mean by that is that if I have, let's say this corresponds to F mu 1, and this corresponds to F mu 2. So this one is just the one you find for the vacuum case. This one corresponds to a sourced Maxwell field. You have some common here. So this is the case of isolation. You can have different solutions. And then, for different solutions, the number of terms you have to add on changes. So every term has a different number of solutions. So that was kind of the missing step one to difficulties. When we did this for originally naive for charge one, we said, oh, this is enough to get the relationship to build this. Because everyone goes, oh, you need a sum of them. And that was kind of the ansatz that we proved. Does that answer your question?
Sorry, and is your sense that you have to can only do this with very special matter, or is it like somehow, or do you think for any problem where you can linearize it, this is going to work somehow, or do we not?
That's an excellent question. So in this case, this only worked for sources that are 1 over r to the n.
Yeah.
That's kind of the special case. So it's an excellent question. That's one thing we don't know. At the moment, at the moment it's looking like it's probably special configurations matter, right? So things that can be linearized. So there are very, very limited examples of non-linear solutions. So in Euclidean space, you can do some sort of double copies of instantons. Only very, very specific types of instantons where your wide number is zero. So very non-interesting, trivial instantons. So at the moment, it seems like very, very special solutions can be double copied, but we're hoping to extend this. There's been some interesting work looking at double copies actually in ADS-CF3 space, like around Gonzalez and friends. So that's kind of an interesting space where they've actually tried to connect it to this conformal field with it. So it's very much as an infancy, we don't know. It'd be nice to do, but at the moment, at the present time, it looks like saying special solutions.
Okay, if there are no further questions, then we should move on to Gus.